In our quest to conquer the cosmos, the speed of light remains an intriguing but elusive concept. The speed of light, constant at 299.792 kilometers per second, is the speed limit of the universe according to Einstein's theory of relativity. It is a towering wall that defies our ambitions of interstellar exploration. In this video, we'll explore some theoretical methods that challenge this barrier, exploring concepts in quantum mechanics, exotic matter, and even time travel, to propose intriguing possibilities of faster-than-light travel. Warp drive, bending the fabric of space-time. The warp drive seeks to exceed the speed of light by bending space-time. According to Einstein's theory of general relativity, massive objects distort space-time, generating gravity. In 1994, the physicist Miguel Alcubierre proposed a mathematical model for this concept. The Alcubierre drive impulse, now called the Alcubierre drive, proposes to create a bubble of distortion around a spaceship, allowing it to move faster than light without violating the laws of physics. However, the Alcubierre impulse faces significant challenges. It requires negative energy or exotic matter, theoretical substances whose existence has not been confirmed. In addition, the energy requirements are enormous, and problems such as causality violations, temporal paradoxes, and destructive tidal forces arise. Despite these challenges, research into warp drive technology continues, fueled by the ability to instantly overcome distances. Advances in quantum physics, dark energy, and exotic matter provide hope that this concept may become a scientific reality in the future. Wormholes, taking shortcuts through space. Wormholes, theoretical shortcuts connecting distant regions of the universe, are postulated on the cosmic highway. These tunnels could allow interstellar and intergalactic travel without exceeding the speed of light. Wormholes would arise from the curvature of space-time according to the equations of general relativity. These holes would be like bridges in the fourth dimension, connecting points in three-dimensional space. Although from our perspective it would seem like an instant jump, in space-time it would not exceed the speed of light. However, the stability of wormholes presents problems. The natural ones would be unstable and would collapse quickly. Keeping a wormhole open would require exotic matter with unusual properties, the existence of which is not yet proven. Creating a wormhole would require manipulating singularities and dealing with quantum gravity, not yet fully understood. Navigating through them would also be a challenge, as they could lead to very different places or times and even to different universes if multiple universes exist. There are risks in going through a wormhole, such as the possibility of feedback and destruction of the hole and the objects that pass through it. Despite the challenges, research on wormholes continues, as they offer fascinating travel possibilities and the chance to marry general relativity with quantum mechanics, which would help us better understand the universe as a whole. Quantum entanglement. Quantum entanglement is an intriguing phenomenon in quantum mechanics that allows for an instantaneous connection between particles, no matter how far apart they are. Although it appears to defy the speed of light, its use for faster travel or communication faces significant obstacles. Quantum entanglement has been verified experimentally and is an established part of quantum theory. Although the possibility of using entanglement for instantaneous communication or quantum teleportation has been raised, there are important limitations. First, entanglement does not allow classical information transfer, since entangled quantum states are not readable until measured, and the results appear random. Second, measuring or manipulating a quantum system generally collapses entanglement, making it difficult to maintain over long distances. Finally, the non-communication theorem in quantum mechanics states that it is impossible to transmit classical information through a quantum channel alone. Although quantum entanglement has applications in quantum computing and cryptography, its utility for faster-than-light travel or communication is highly unlikely based on our current understanding. Although it is fascinating for the understanding of the quantum world, its practical application in this sense faces insurmountable challenges. The hypothetical tachyans. Tachyans are hypothetical particles that could travel faster than light. Its name comes from the Greek word tachys, which means fast. According to special relativity and quantum field theory, tachyans have peculiar properties. Unlike normal particles called bradyons, which would require infinite energy to reach the speed of light, tachyans would require infinite energy to slow down to light. This is because an imaginary or negative mass is attributed to them. Tachyans have opposite behaviors to normal particles. They speed up when they lose energy and would appear to experience time in reverse from our perspective. However, its existence poses complications and paradoxes, such as the violation of causality. Although evidence of tachyans has been searched for decades, none has been found. The phenomena attributed to them in the past turned out to be experimental errors. Their appearance in a theory usually indicates instability. In short, tachyans are speculative, and there is no consensus on their existence among physicists. Based on our current understanding of the laws of physics, faster-than-light particles are unlikely to exist. However, if proven otherwise in the future, it would require fundamental changes to our current theories. Negative energy as fuel for faster-than-light travel. Negative energy, an intriguing concept stemming from quantum physics and general relativity, could be the key to faster-than-light travel. Although in classical physics negative energy does not exist, in quantum mechanics it is allowed under certain conditions. An example of negative energy is the Casimir effect, where two uncharged metal plates experience an attractive force due to the presence of negative energy between them in a vacuum. Negative energy is applied in faster-than-light travel, such as warp drives and wormholes. The Alcubierre drive, for example, uses negative energy to create a bubble of warped spacetime and move at superluminal speeds. However, the use of negative energy presents significant challenges. First, the production and stabilization of a significant amount of negative energy over the long term is currently unattainable. In addition, its existence raises concerns about the violation of fundamental energy conditions and the possibility of paradoxical effects, such as time travel or the creation of perpetual motion machines. Furthermore, the principle of quantum interest suggests that accumulating negative energy leads to the generation of massive pulses of positive energy, nullifying the desired effect. Despite these challenges, negative energy research continues to inspire scientists. Although we do not yet fully understand its nature, its study could have a revolutionary impact on space travel and energy production. Defeating the light through time travel. Time travel involves moving through time instead of exceeding the speed of light. According to Einstein, time and space are intertwined in space-time. Gravity bends space-time and affects the trajectory of objects and the flow of time. Traveling to the future would theoretically be possible by approaching light speed or massive objects, slowing down time for the traveler. However, traveling to the past is more complex and would require closed curves of time. Some solutions to Einstein's equations suggest the possibility of travel into the past, but these solutions are specific and require particular conditions. In addition, travel to the past presents problems such as causality violations and paradoxes. Some physicists propose that quantum mechanics and the Novikov self-consistency principle could avoid these paradoxes, but this is speculative and many physicists are skeptical. A theory of quantum gravity is expected to provide clearer answers about the feasibility of time travel. The concept of time travel raises fascinating questions about reality, causation, and the nature of time from a scientific and philosophical perspective.